Okay, so how do we think about this problem? One thing is we can go through the technical exercise of doing the calculation like I did in class last time. And what we have in this problem is we have 5 copies of this problem. So this was the one I did in class. This is anchored, and I'm going to pull on this thing. But now this thing is being pulled with another copy of the same, which is being pulled with another copy of the same. So if we want to work out this problem of the string lengths, we have to write the length of this string as constant, and that will tell us the relationship between this motion and this motion. And what you find out is this moves twice as much as this moves, and we worked that out last time, and you can see that that's true. The pulley moves half as much as the block moves. And that's going to be true for the next copy, and the next copy, and the next copy. So this moves half as much as this does. This moves half as much as that does. This moves half as much as that does, and so on. And we've got 5 copies of that. So this moves 2 to the 5th less than this moves. Now that's the kinematic relationship between these two. So this is a motion amplifier. Because if I put in a small motion here, I get back 2 to the 5th times as much motion here. So if we put in some motion here, this moves 2 to the 5th times as much. So it looks like maybe we're going to get a big number out of this thing. But what happens is if we do the force analysis, if we treat these as massless pulleys, these 2 tensions add up to this one. So the tension in this rope is half of this force. The tension in this one is half of that tension, and so on. So the tension here is 2 to the 5th times smaller than this force here. 2 to the 5th is 32. Okay, so this force is 1/32 of this force, the force on this mass. This thing then has an acceleration of F over m divided by 32. Right? This one moves half as much as this does. So we divide by 2 again, and we divide by 2 again, divide by 2 again, 2 to the 5th again. So that means the acceleration of this point is 1/1000th. That's 32 squared. Okay, 1024. 1/1000th of F divided by m. So the right answer here is A, and which some of you got. A. We'll get there yet. A. Okay, any questions about that? Yes? Question? Yes?
What was the last part of how you went from finding acceleration at point A to getting to acceleration?
Okay, so there's 2 different analyses you can do with pulleys. One is the kinematic analysis, and one is the force analysis. The force, the force analysis is based on the tension in a given rope being constant along its length. Tension on 2 sides of a pulley is the same. That comes from a statics calculation, which you can read about in the statics book or think about moment balance. The kinematics calculation says that the length of a string is constant. So that the length of this string is constant makes it so that this thing moves half as much as this one. It has half the displacement, half the velocity, and half the acceleration. And we can see that over here. First of all, you can do it, just look at the notes from lecture last time in the video, or you can look at this thing and say, if this moves a little bit, the pulley over here, how much does the block move? The block moves twice as much. Or if the block moves a little bit, how much does the pulley move? So let's move the block a little bit. The pulley would move that much, but it can't because it's tied to this rope here. So it has to give up rope here in order to move. Okay, or you just look at it like this. And you can do this experiment in your dorm room with shoelaces and paper clips and your teeth and stuff like that. You should play with string and you to get a feel for this. The key intuition you want to work on is that if you have a device like this is a motion amplifier, in that when I put in a little motion here, it gives a big motion here. any device which is a motion amplifier and is a passive device, it doesn't have gasoline in it, has to be a force attenuator. So the fact that this thing moves twice as much but only has half the tension on it is not a coincidence. Why isn't it a coincidence? Is because if I put in some work here, some force times distance, this system is a passive system. It doesn't absorb or generate energy. That work has to get to here. So if a certain force times distance or force velocity goes in here, that force times velocity has to come out here. So if the velocity is bigger, the force has to be smaller. If the velocity is smaller, the force has to be bigger. So this duality between force and displacement has to be there. And as I said last time, if you're just looking at it at the beginning, you think of things as a pulley as being an amplifier, and it's a cloud in your head, whether it's force or displacement, and you want to untangle that cloud because they're actually reciprocal concepts. Okay, any other questions about that? Yes?
So that setup there creates more speed. What would a setup that creates more force look like?
Ready? Does that answer your question?
Yes.
Was that the question for the video? Was how could you make a system that would multiply force instead of multiplying speed? The reciprocal system does the reciprocal thing. Any other questions? Yes?
I follow how you got the sort of production of speed through kinematics, but why was the 1/32 done again and again?
We had factor of 32 two times, one from the kinematics and one from the force. Now we know it has to be the same factor of 32 by the fact that this is an energy passive system, so the power into the system has to be the power out. So the force times displacement getting to this mass has to be the same as the force times displacement coming from this force. Do you mind if I do this new problem instead of erasing again? And this is going to be backwards. The answer is going to be 1,000 to this problem, right? Okay, so let's take this problem. The kinematic analysis says this thing moves half as much as this does. This moves half as much as that, and so on. So this moves 1/32 times as much as this does. You're happy with that? Okay. So this is a motion attenuator. This is the usual way you use a pulley if you want to generate a giant force from a small force. What about the force amplifier aspect of it, which is why you use pulleys usually, is to amplify forces? Here we have a tension in this string and a tension in this string. If we draw a free body diagram of this pulley, we cut the universe free from this. We have a tension here, and a tension here. For these to add up, this tension has to be twice as big as this one. And then you do the next one here, this one has to be twice as big as this one, and we get the factor of 32 multiplication in the force. Okay? So the length calculation gives you the attenuation of displacement. The force calculation gives you the multiplication of force. And the power equation says that those two have to give the same answer. Does that address your question? Okay. So now, you were okay on video, James? Okay. Today we're going to go on with 1D motion with constraints. The first example is pulleys, and then I'll show you another example. Then we want to move on to two-dimensional problems. Overall, what's happening in the course is we're moving from being worried about time to being worried about space. So for the most part, at the beginning of the semester, we've been doing differential equations, watching how things evolve in time. Now we're going to go back and do more statics-like things, statics-like in skills, and worry about geometry and how things are oriented, and not pay so much attention to how they evolve in time, at least for a while. So we're doing kinematic constraints. What do we mean by kinematic? Kinematic means geometric. Constraint means it's a restriction on the geometry. So these are restrictions on motion. So the example that we've got so far is this pulley examples. And what's the constraint? The constraint that we're dealing with is that the string length or the string lengths are constant. Now I did two examples in class corresponding to these examples with this pulley pulling two different ways, which gives you the essence of the thing. I didn't do any hard examples. You should certainly master the 3 examples I did in lecture last time. I only did out 2 of them. One of them is trivial, before you go on. And then for the homework, you have to do harder problems. I'm going to skip doing a harder example in a lecture, but there's harder examples in the text. So see text for more complex examples. Okay, let me just show another example, which is kind of a trivial example. It's maybe too trivial to be revealing, but if you, I just want to show it as sort of the simplest example. So let's say I have 2 masses, and they're connected by a string, and then I'm going to pull them with some force F, and I'm interested in knowing what's the acceleration of the system and what's the tension in the string. Now, if all I want to know is the acceleration in the system, I could just treat this pair of particles as a single particle and just say the acceleration is the force divided by the sum of the masses. But let's say I want to know the tension in this string. What is the tension in this string here? How are we going to work that out? So one way we can deal with this is we can draw free-body diagrams. There are 3 conceivable free-body diagrams. I'm just going to draw 2 of them. I'm going to draw this one and this one. I'll cut this string, and when I cut this string, there's some tension in it. Over here, it's the same string. We're going to neglect the mass of the string itself. So for the string, we'll do statics. Therefore, this tension is equal to that tension. Force balances on the string. If we wanted to include the mass of the string, that would be a different problem. And then we also have this force F, which is applied to just the right-hand mass. Then if we look at linear momentum balance for this system, we have here that mx1 double dot is equal to the tension. And over here we have m2 times x2 double dot is equal to the force minus the tension. Now, can we solve for the tension and the accelerations from those equations? Yes? No? Yes? What's your question? You have an answer for me?
Well, we also have to say that force, like what mx double dot,
we could put these together, and we can get that m1 x1 double dot plus m2 x2 double dot is equal to F. That's what we get if we add those 2 equations. It's also what we would get if we drew a free body diagram of the whole system and just use linear momentum balance for the whole system. So we can write that. That's okay. Yes?
So what do they get net acceleration of the whole system?
Well, so that's the thing, is we have to say the acceleration is the same of the system. What do we mean? Is all the different parts have the same acceleration. So that's the constraint equation. So that's the idea here, is that in order to solve this problem, somehow we have to put in this information, which is that x1 double dot is equal to x2 double dot. So this set of things, any 2 of these equations gives us 2 equations, and this gives us 1 equation, and altogether then we have 3 equations for x1 double dot, x2 double dot, and the tension. Now, this is such an easy problem that you can work your way around it without setting it up with these 3 equations. For example, we could have just started with this equation. We wouldn't have even bothered to call this x1 and x2. We would have just called it x double dot, because obviously these 2 move the same amount. We could have found the net acceleration. After we did that, then we would look at this free body diagram. We know the acceleration. We could calculate the tension. And we wouldn't have noticed that we have this issue. The point I'm trying to make here is for a problem like this, somehow or other, you have to put in the information that there's a kinematic constraint here, which we need to solve the problem. And this is in some form or other what we're going to be doing now for a long time, is somehow we have to put information about the constraints into the problem in order to get an answer. Okay, so let me go on and do a 2D problem. And again, it's an easy problem. certainly of the type that you could have done in physics in high school or physics 112. And I'm going to call this a particle problem. So we're not going to still, at this point, not till later in the lecture, worried about the spatial extent of this thing. And let's just say I have a rod here. And on this rod, I've got some bead. And I'm going to pull on this bead with some tension at some angle theta. Or I can keep track of that direction with some unit vector n. If I need it, I can have some unit vector lambda perpendicular to that. On the side here, I can have my standard x and y unit vectors. Let's say this has some mass. This thing is anchored to the ground. We're going to pay attention to the x coordinate in that direction, and the same as the I direction. And we want to know various things. Now, what are the things we could want to know here? We could want to know what is the, given the tension, what's the acceleration of this bead? And this one you can do in your head, obviously. The acceleration of this thing along this rod is the projection of this force in this direction, so it's t cosine theta, and then we divide by the mass, it gives us that acceleration. What else might we want to know is what is the constraint force? And what do we mean by the constraint force? This thing is a constraint because it enforces this thing to move in this one direction, in this one dimensional motion. So if we draw a free body diagram of this thing, we can add g to this to make it more complicated looking. We have our bead here, and we have acting on it mg, and we have acting on it some normal force. Probably that n will turn out to be a negative number, but some force which is perpendicular to the rod. And then we also have here some tension force in the direction that is given. So this thing is what we would call a constraint force. It's the force it takes to keep the bead on the wire. So if we now want to do this problem more formally, getting our answer that the acceleration is t cos theta divided by m, we can take that free body diagram, write linear momentum balance for this system. And linear momentum balance says that the sum of all the forces is equal to the rate of change of linear momentum. What are all the forces? I've got n minus mg multiplied by j. I have a plus t multiplied by lambda, or I could break that into x and y components and put I and j there. And I've got this is equal to the mass times the acceleration. And now I'm going to put in the kinematic constraint equation here by saying that the acceleration is equal to x double dot I. It's got no y component. It's constrained to move in the x direction. So I put in the constraint at this point. Now I'd like to figure out what's going on. If I say t is given, can I figure out what's going on? And the answer is I can, because if I take this equation, let me call this equation 1. 1 is 2 equations for what? For x double dot and for this n. So we can solve for that n. Is n equal to mg? Quick raise of hands. N is equal to mg? Yes? No? Raise your hand. Obviously, good. So we can solve those equations. Use the fact that, how do we solve the equations? By taking this thing, dotting it with I, and getting one scalar equation, taking that big equation dot with j, get another scalar equation. That just means take this equation here and take the x and y components. But x and y components are equivalent to dotting with I and j. And this will then tell us that x double dot is equal to t cosine theta over m. And it'll tell us that n is equal to m g. That's going up minus t sine theta. Now, just for fun, what if we wanted to know n, but we didn't care about the acceleration? Could we find n, and just rather than having to solve two equations and two unknowns, could we find n all in one shot from one scalar equation? Yes?
We can use some forces.
Okay, if we just sum forces in the y direction, we would find n. That's right. But what do we mean by summing forces in the y direction? We mean take linear momentum balance in the y direction, and there's no inertial term because we assume the acceleration in the y direction is 0. So you have to be careful with the language. Okay, so now let me go on and do a substantially harder problem, and one that's a little bit interesting. And all of a sudden, we're now going to really dive into the world of vectors. So this problem is the car braking problem. Car braking. And we're going to do, as an example, front wheel braking. So let me draw a picture of the system. And then try and work out what's going on. So we're going to have a car. And this car is going to be on level ground like so. And it's going to look like so. Doesn't look much like a car, does it? There, it looks more like a car now. Somewhere in this car, there's a center of mass. Let's call this point G the center of mass. We've got to worry about various dimensions of this car. So let's call this dimension D, this dimension E. We can call this dimension L, which is D plus E. This center of mass is up here some distance h. Let's say the car is zooming along here with speed v. And the car is going to stop. And it's going to stop by screeching on the front brakes. So we're going to have front wheel braking. So let's put in some assumptions here to make it so we can manage this problem. And they're not bad assumptions. Let's assume a stiff suspension. So what do we mean by assuming a stiff suspension? When you screech the brakes, somehow the car is going to sort of lurch a little bit, and somehow intuitively you think there's more weight on the front wheel, and the springs are going to compress, and the car is going to rotate a little bit. Let's neglect that rotation. So let's assume that when you screech on the brakes, the car's orientation does not change because the springs are stiff. Let's assume that the wheels have negligible mass. What does that mean is that as far as the inertia part of this problem, the MA part of this problem, we don't worry about the fact that the wheels are turning or the different parts of this car have different acceleration. Let's assume that the front wheel skids with friction mu. Now, an alternative to that is we could say it skids with a friction angle in the friction force of phi. So we can either specify phi or mu. So we're going to think as given the geometry will be given, say, the speed that is going forward. We're given the mass, and we're given mu or phi. And we want to figure out what? How fast this thing decelerates. Now, can you just do this in your head? So a calculation you might want to do, if you were going to do it in your head, is you would say, we're going to be given G, of course, too. You might say, well, let's look. This is sort of like a mass supported by 2 points. If E is smaller than D, there's more weight on the front wheel. In fact, when the car is sitting here, if it's just sitting still, the vertical force here is D divided by L times mg. And then we multiply that by mu, it tells us the friction force. And then we divide by the mass, it tells us the acceleration. That's a wrong calculation. What's wrong with that calculation is that this is a dynamics problem, and we can't use the statics calculation to figure out the proportion of the normal forces on the two wheels. The sum of forces and sum of moments don't add to 0. And the reasoning which gives you that the weight on the wheels is proportional to those distances was based on statics reasoning. So that's a wrong answer. So that means we actually have to do a dynamics calculation. Okay, so how are we going to do that? We'll start out by drawing a free body diagram, and then we'll write the laws of mechanics. So what does the free body diagram look like? Well, we don't have to draw in great detail everything. We just draw a car. All we need to do is we make sure we get the key points on the picture. For example, here's a key point A, here's a key point B, here's a key point G, and we now need to put what are the forces on these key points. So we've got here the weight of the car, and the claim is, left over from statics, that all of the gravity forces on all of the atoms of the car are statically equivalent, or mechanically equivalent, or equipolant, or equivalent to a single force acting at the center of gravity. What else do we have? Well, let's assume the rear wheel has good bearings, and we're not using rear wheel braking, we're only slamming on the brakes in the front wheel. Moment balance about the center of the wheel tells us that the reaction force in the ground has to point through the center of the wheel. Why can we use moment balance when we're doing a dynamics problem is because we said the wheel has negligible mass. So the inertial effects of the wheel we think of as negligible. Not too bad of an approximation. So let me just call this NA, and here we have our point A. We've separated out the ground. Cutting away the ground, we also have to show what kept the car from going through to the earth like this. And then we also have a friction force at B, F sub B. And this is the whole free body diagram. It looks just like it would look in statics. And off on the side, we can show that we know the dimensions of things like this. And we know the height of this thing over here is h like this. But these are little small arrows that we don't confuse with these big force arrows on this free body diagram. Okay, any questions about this free body diagram? Okay, so you have a question? Yes? So what we assume back here is that we're doing front wheel braking and that the rear wheel has good bearings and has no brake on it. Now, again, in your head, you might be thinking, if the car is slowing down, then the angular velocity of that rear wheel is decreasing. What force is causing it to decrease? Well, it is a sideways force on this wheel which causes the angular velocity of this rear wheel to decrease. But the less the mass of the wheel, the smaller that force. And if we neglect the mass of that wheel, that's like assuming that force is close enough to 0 to be neglected. Didn't you ask the same question last class? Somebody back there asked that about the pulley. Okay. So what do we have to work with in terms of solving this problem is the equations of mechanics. And the first equation we have to work with is the same equation we've been working with all the time, which is linear momentum balance. So we have linear momentum balance, which says that the sum of the forces on this system is equal to the rate of change of the linear momentum of the system. What are the forces on this system? Well, we have NA up plus NB up minus MG down, all in the J direction. And we have to add to that a minus f in the b direction, sorry, minus fb in the I direction, and this is equal to the rate of change of linear momentum of this system. Now, for any system, no matter how complicated it is, the rate of change of linear momentum is the sum of the rates of change of all the parts. Too complicated. Here we just have a simple rigid object. It's easier to use another form, which is true for every system, which is the rate of change of linear momentum is that which you get by thinking of the system as a particle at the center of mass. Or it's the total mass of the system times the acceleration of the center of mass. And that's true for any system, no matter how complicated and no matter how it moves. One rigid object is a deformable object, a collection of particles, a blob of fluid, whatever. Then we can put in our kinematic assumption that the acceleration of g is just equal to x double dot times I. Or we can just, I'll just call it, it's a scalar, the acceleration of g in the I direction. So that's the kinematic assumption, or the constraint that the acceleration is just a translation in this direction. The car's not tipping over, it's not spinning, it's not jumping up and down, it's not falling through the earth. Okay, if we call this equation 1, then 1 is two scalar equations. It's a vector equation, and it's two scalar equations for, what do we have as unknowns? We have NA, we have NB, we have the friction force at B, and we have the acceleration of the car, or acceleration of G. So we have four unknowns. So certainly we cannot find all these unknowns from just these two equations. What do I mean by two equations? I mean take this equation and dot it with I and dot it with J. Or dot it with any two non-parallel vectors you like, you get two independent scalar equations. Okay, so we need more equations. What else do we have? Well, we have the friction equation. The friction equation says that FB is equal to mu NB. So we're going, that's assuming skidding. So we've assumed that we've slammed on the brakes and the front wheel is skidding. If you haven't slammed on the brakes, then we don't know what that friction force is. We can't solve the problem because we don't know how hard the person's pushing on the gas pedal, on the brake pedal, sorry. We can't get an answer because it depends on things that we don't know. So to make it solvable, we have to assume something about the force. Let's assume it's a skidding force. Okay, so now we're up to one more equation. This is one equation. We need something more to solve this problem. What more do we have to work with? So you can think about that for a minute while I erase the board. Okay, now you've thought about it. What more do I have to work with to solve this problem? Not you. Somebody, I got a challenge for you guys, okay. New vote here. Vote A if you've asked 2 or more questions in this semester so far. B if you've asked one question or answered one question. And C if you've never asked or answered a question in lecture out loud. And all the lectures this semester. And D if you've never asked or answered a question out loud in any lecture at Cornell. Okay, so I'd like to set a rule for today's lecture. It's a rule for the indefinite future. When I ask you guys for answers, I only want answers from this category of people. Okay, I want you to stretch your limits here. Come out of your shell. Admit that you're here in the room with us. Join the crowd. Okay. You got to be kidding.
Wait, didn't you just tell us to ask questions, or did you tell us not to ask questions?
Now, a different thing I might ask you to do is pay attention in lecture. But let's just skip that. Okay, I want questions for people who have not asked questions before. Okay, so of you who've never asked questions before, can you answer this question? We're now trying to figure out how this car goes, and we want to figure out how much it decelerates when we slam on the brakes. How are we going to figure it out? We draw a Freebody diagram. We use what we know, say that there's a friction relation, so we know that the friction force at the front wheel is mu times the normal force, but we don't know the normal force of the front wheel, and we can't use statics reasoning to find it. So we have a friction equation. We use linear momentum balance. The total force is mass times acceleration. It's a 2D problem. That gives us two equations. But we have four unknowns. So we need something else. Now, if you've never asked a question in class before, really go for it then. Office hours. I know you. Okay, go on. Okay, go for it. Good.
Is it the constraint that the acceleration of the center of gravity is
In the x direction. So we've already used that here. So if I didn't use that, I would actually have five unknowns. I'd have a vertical acceleration and a horizontal acceleration. So by reducing this to a single unknown, I've already used the constraint that it's moving in the x direction. Yes?
Can you take the moment above point B?
Can we take the moment about point B? Well, any force system, you can take moments about any point. We need to turn that into an equation.
Like a statics problem?
But it's not a statics problem.
But then isn't the acceleration above the component 0?
Yes, but it's not a statics problem. So everything you're saying is almost right. Your intuition is right. Now, are you a legitimate answerer?
Yeah.
Go ahead, go for it.
You do angular momentum.
Angular momentum balance. So this is our big equation. And this is all for the rest of the semester. We're going to be using angular momentum balance again and again and again. And here is our first real use of it. For the particle motion of the planets, we had the angular momentum is conserved for central force motion. But we didn't really make much use of that equation. Here, we're really going to use that equation. So what we're going to say is we're going to have this equation, which we're going to call angular momentum balance. And this is analogous to moment balance in statics. It's more than analogous. Moment balance in statics is a special case of angular momentum balance in dynamics. Angular momentum balance then is going to say, this is angular momentum balance. I won't write it out. It says that the sum of moments relative to any point we want, and I can call this point C. C is good because I don't have any C on the picture, so I can use C for anything I want, is equal to the rate of change of angular momentum with respect to any point C. This is a much more subtle equation than the momentum balance equation. What we mean by with respect to is a subtle thing. To start with, you can think of point C as any fixed point in space. Now, it's not literally true that it has to be that, but this is a tough thing because here we have this car moving along, and what do we mean by a fixed point in space? So what we have to do is we're going to use angular momentum balance about a fixed point in space that instantaneously coincides with some point of interest in the car. Now, what point can we use? We can use any point C. Now, what would be a convenient point to use for this problem is the point B. Why is point B a convenient point? Because there's two forces there. None of those forces have any moments. Our calculation is simpler if we pick a point that eliminates things which we just make the equation simpler. It drops terms out of the equation. So we can use point B, but really any point would do. For this problem, no matter what point we picked, we'd have a third independent equation, and we'd be able to solve. If we use point B, we therefore write angular momentum balance, and we say angular momentum balance with respect to B. That says that the sum of moments with respect to B is equal to the rate of change of angular momentum with respect to B. And now we need to fill in the left-hand side and the right-hand side. Now the left-hand side gets filled in exactly, precisely the way you would do it in statics. Look at the free body diagram, pretend it's a statics problem. The difference is we're not going to put 0 on the right-hand side. We're going to put something else. Let's just do the left-hand side. What do we have? We have the position of point A with respect to B, crossed with the force at A, which was NAJ. And we have the position of G with respect to B, crossed with the force at G, which was minus MGJ. And those are the only two forces which show up in this problem. Because with respect to point B, the forces at B don't show up. What are these two position vectors? This is minus EI plus HJ. What's this position vector here? It's minus LI. L is not really independent of E and D, but it saves writing to write it like this. So we know how to evaluate the whole left-hand side. We don't know the answer because we don't know what this force is, but we know how to evaluate all these terms. On the right-hand side, we have now the rate of change of angular momentum with respect to a point B on the ground, instantaneously coinciding with where the car is at this instant. So now we have the simplest case of evaluating angular momentum balance. This is R of G with respect to point B, crossed with the mass times the acceleration of point B, of point G. That's the thing we called AGI. AGI is going to turn out to be AG is going to turn out to be a negative number, plus 0. So at this point, this is all that shows up on the right-hand side. Now, from freshman physics, you're used to angular momentum balance being about I omega and stuff like that. But that's only if you have one rigid object which is doing nothing but rotating. J omega dot, I alpha, J alpha, whatever it is. Now we've got something which is moving around, and we're taking angular momentum balance not with respect to the center of mass, but some other point. And the angular momentum balance has two terms in it. One associated with motion of the center of mass, and one associated with motion relative to the center of mass. But in this problem, where the car moves as a rigid object, and it has no rotation, that second term is 0. So for a rigid object which only translates, the rate of change of angular momentum is the same as you would get as if it was a particle. And for a particle, it's just R cross MA. Okay, now we know what this term is also. We can take this equation and we can dot it with what if we want to get a scalar equation out of it. You're not allowed to talk. You're not even allowed to ask a question. Ask somebody next to you to ask a question. Yes?
What is the 0?
What is the 0 about? Nothing. Okay. That's a joke I saw in a movie one time. It's about nothing. It's about the history of science, the history of humanity all in 1 minute. In the middle of the movie, somebody goes, 5,000 years ago, he goes, I've invented the 0. And somebody says, what? He goes, oh, nothing. Okay, what's the 0 about? It's about the motion relative to the center of mass. And that's a term which we're going to be filling in harder problems later on where objects are rotating. Yes?
So the 0 comes from the first term of the left-hand side, not going to 0, or going to 0?
The 0 has to do with things we haven't talked about yet this semester. The general formula for rate of change of angular momentum of a system has two terms in it, one of which is 0 now. The second term has to do with what happens if the object is rotating, or what happens if the object is distorting and has parts which move relative to each other. Okay, if we dot this with K, this gives us one equation, and we then have 4 equations and 4 unknowns, and we can solve. 4 equations and 4 unknowns you might find annoying. If you want to do this problem quick and just get, for example, the acceleration of the car all in one shot, what you could do is draw the free body diagram like this. Instead of drawing the free body diagram with a vertical force and a horizontal one, we know what this coefficient of friction is, so we know this friction angle. We can go up here and find this point here, E, and if we take and use angular momentum balance about this point E, these two forces drop out, which we don't know. This one stays in, which we do know. The acceleration stays in, which we don't know. So a shortcut for this problem is if we take angular momentum balance with respect to point E, that's a vector equation. Take the dot product of that with K. In 2 dimensions, all moment equations end up being vector equations in the K direction, only one non-zero component. This will just give us the acceleration of G in one equation. And I believe class is over. Is that correct? So I realized a jarring thing happened today. All of a sudden, we're back in the world of vectors. I didn't really brace you for it, but now all those static skills, you've got to kick in a big way. Okay, so go for it.